So welcome everybody to today's session. Today I'm going to talk about syntax-aware cross-modal retrieval. And as probably you know me already, or some of them know, I'm a PhD student under the direction of Dimos and Lluis Gómez. So on this very first task, we began with the question, does incidental syntax could help for cross-modal retrieval? So as we can see, for instance, on the figure, right? We have a query, which is a group of people eating pizza. So it's very important to know the pizza word, which is very important in this specific context, because it plays a very discriminative role, right? Even though both images that are retrieved by this system are correct in the sense that you can see some people eating in a restaurant and so on, but basically the word pizza could find fine-grain, let's say, your retrieval and improve the performance of such a system according to your needs. No, so the whole task basically is to define some visual features that could be modified by your specific syntax, let's say, that is encapsulated in your query. And so this way you can more or less model a much richer and fine-grained space. So the problem that we stumbled at that point is that we couldn't find any data set that contain all these three modalities required for this task, which is images, captions, and syntax. So we start looking in MS COCO. Maybe you're familiar with it. And basically it's a common data set used in object detection, segmentation, and so forth. So basically we used COCO text, which is a subset of MS COCO. It contains more or less 60,000 images, and 50% of them contains syntax already. So it's a good proxy task and a good data set that we can start working on with. An important thing to note is that COCO text, since it's a subset of MS COCO, was not considering syntax when the images were included in the data set. So this more or less models the real life distribution on the world, let's say, of syntax appearances. And it's very interesting how to model this specific syntax into a cross-modal retrieval pipeline. An important thing to note is that OCR models usually do not perform that good in this data set, so it's not that easy, since also it's not taking in consideration very specifically the syntax that you can find in an image. Rather, it comes from, let's say, natural, more natural and improvised photographs. So as you can see, some samples of these COCO text dataset are on the right. And on the bottom, you can see some legible English and machine printed syntax in COCO text, which is the criteria that we use to filter out. So going back just to briefly explain the diagram, so just to have it clear, we have COCO captions on the left, which is a very big dataset, right? COCO text on the right, which is a subset of COCO text. And basically, we just consider the three modalities that we're interested in modeling, right? So finally, we end up with images, caption, and syntax annotations. So the very first model that we began with working, it is inspired on a cross-modal retrieval pipeline and also addresses a very specific task. So it's a little bit different to common vision and language models, which are very more or less, they are formed by a very big transformer. In this case, we just have a very task-specific model. So in this case, we have some visual features coming from a faster RCNN. This faster RCNN is pre-trained on visual genome, and rather than predicting only some very specific object that is contained in the image, it also predicts some adjectives and some other descriptions that can reach these features, right? So at the end of passing these images through a faster RCNN, we end up with visual regions coming from bounding boxes and some features, okay? Then, as I explained on the previous talk, in the previous session on Monday, we use a graph convolutional neural network to enrich the interplay among these visual regions, okay? So each visual region will be enriched according to the correlation that the model finds within the data. And later, these enriched representations are going to be passed on a GRU. Okay, this GRU in this case is used to more or less find a final representation of all these vision regions. Okay, considering the whole relationship among them. So as OCR, in this case, we used Google OCR, and the text features are extracted as well and as modeled with fast text. So if you can remember, fast text takes in consideration the n-gram of each word as well as the semantics. So in this manner, we more or less exploit the best of both worlds, right? We also use a dedicated text graph convolutional network, which basically will form richer representations of the text, and it will correlate the most important syntax tokens. So at the end, we end up with a matrix, which represents the syntax of our image. We take the average pooling of it, okay, and we obtain a final representation. So it's quite common in the field of image modifiers. Basically, you can modify an image with an object, drawing, or text. But usually you treat these modifiers as some different distortion that the original image has. So in this case, we fuse both modalities, syntax and visual features, using text as a modifier of the image, right? So whenever the image ends up in this space, whatever the syntax does to it, it will kind of point it to enrich them according to the relationship between these two modalities. And we try to anchor with the caption. So at the end, we end up with a final image representation, IFI, right? And basically, we use some captions, which comes from a different modality, to construct a triplet loss, okay? So what we try to do is to map the images, okay? And learn a semantic space given by some margin, which will get positive samples close to each other and hard samples or negative samples above this specific margin, okay? And as a proxy task that we found out that improved the representation learned is basically given the visual features, IFI, we produce captions and we use the original caption as a ground truth, okay? Finally, we train this model on Flickr 30K, which is a dataset that do not contain any syntax. Then we also use TextCaps, which is a dataset that is very focused on syntax. Basically, on this dataset, the task is to come up with captions given the syntax that appears in the image. And this proposed CTC dataset, which is more or less balanced, right? So it's kind of like the best of both worlds, let's say, or let's bias on just visual features or just syntax. And as a final model, it comes from a paper from Baidu. It's published on DCVPR 2022. And they propose a big transformer to do this task, right? So as an interesting thing, they fuse the syntax and visual features in a novel way. And I will explain it a little bit further, but it's important to note how they encode each modality to the transformer. So they use a modality-specific token. In this case, it's in gray. So for visual features, you have M sub 0, right? Then you add some positional encoding, the standard cosine and sinusoidal waveform, let's say, that transformers use. And we use this with the patches coming from the image, okay? So basically you take each image, cut it or patch it, take the patches according to some specific size of the pixels. We flatten them and we pass it through a vision encoder, right? Then basically they use a BERT, which is a bidirectional model. It was briefly explained by Ernest in the previous session. And what they do is take each token, right, coming from the text descriptions and pass it through this text embedding, which is a linear projection layer. We also append the different modality token, right? And we use as well as a positional encoder. And finally, the syntax encoder, they just take an image, pass it through an OCR. They get the descriptions of this OCR, which is the text the text recognitions of this image. And they use a positional encoder that comes basically from the positional bounding boxes of the text. And we also use another modality, M1, that represents the syntax. And they pass it through this encoder, which is a BERT model at the end. So how do they fuse these two modalities? It's quite interesting. So basically, they have an NN parameter, which is in PyTorch, let's say. So you just come up with a random vector initialized at the beginning of the training, and you fine tune and learn the correct parameters of this vector in order to properly adapt and represent these two modalities. No? At the end, they end up with the fusion token, which is at the top of this image, right? And this is the representation that you will be using with a contrastive loss to match it up with the captions coming from the BERT text transformer, okay? As a proxy task, they found out that using the CLS token of the vision encoder with the captions coming from the text transformer eventually end up improving the representation, no? So more detailed, and this is how they fuse the both modalities. So in this case, F sub L represents the NN parameter, which is, as I said, the learned token, right, to fuse these two modalities. Then they use a modality, an encoder independent embedding, basically. So this token adds to all the tokens on the vision transformer and on the syntax transformer. Then the summation is done. And the final representation is used with the contrastive loss to perform syntax retrieval. And as we can see also, this model at the end achieves state of the art on this specific task. And it's quite interesting how they model this fusion scheme. No? I'm showing some retrieval results. In this case, you have a text query. So basically, the whole task is given a caption. You have to retrieve the most relevant images, and the other way around, no? So in this case, the first row represents a model that is not able to read. So as you can see, the top one results do not include any syntax that is present on the caption, right? However, on the second row, you can see the top one retrieved result takes into consideration the year that this query is talking about. Also, on the right, you can see the text query, which is a person holding a gummy hot dog in their hand. So gummy hot dog is a very specific discriminative information that you want to use in your retrieval, right? And you can see that the top one result do not contain this gummy hot dog specific brand, right? So whatever it is, eventually, whenever the model is able to read, the performance is way more accurate and fine-grained, no? And some retrieval results. So basically, on the other scenario, let's say, given an image, the model has to retrieve the most closest captions. So you can see, for instance, on the left part, right? So given the image that it's clearly a bus that says Santa Lucia, right? Whenever the model is able to read, the first retrieved sample is a Santa Lucia bus is driving down the road, right? So this Santa Lucia information as well is super important in this retrieval scenario, whereas a model that cannot read is not able to properly retrieve this very specific sample that the user wants to obtain, right? The same is happening on the image on the right, right? If you just put this airplane picture into a retrieval model, the model will have to, in theory, be able to discriminate and read that this specific image is coming from a China Airlines airplane, right? So this is a very important detail that current models, in my opinion, should take into consideration. So final remarks on cross-modal retrieval and some open challenges. Basically, there is a lack of datasets that contain these three unbiased modalities, right? While at the same time being correctly annotated. Usually the problem that models have nowadays is that, the main problem is that syntax is not either present on the captions, right? Or there are datasets that are quite big, but syntax is very specific and has to be included in the caption. So we don't have this middle ground that kind of models real life scenarios. So also the proposed CTC dataset is it's a small but refined dataset. It's dataset where captions and syntax information is independently annotated. No, and as a very brief message to all of you, despite the semantic value of syntax, we have to treat it as a very fine-grained element because it has different types of interactions. No, as it was described briefly, and basically the syntax tokens that we retrieve should be used very selectively and in a well-planned strategy. Okay, so with this, my presentation ends. Thank you very much. Any questions or any comments? Otherwise, we will continue with the next presentation.
Andrés, there is a couple of questions in the chat. Which is the output of the graph of the GCN in the stack-MR?
Sure, let me check the question. So cool. So the question is by Miguel, and he says, which is the output of the GCNs in the stack-MR? So the output of the GCNs basically is an enriched representation of the visual features and the syntax tokens. Let me share again the screen so I can explain this a little bit better. So at the end of the GCN, right, as input features, we'll have the features of the syntax, which in this graph will be modeled as nodes, right? And the edges basically are the relation that the network itself finds among these tokens. And at the end, you will have an enriched representation of these syntax features, which at the end is a matrix with, let's say, n times dimension of the syntax tokens. And the same happens with the visual regions. Okay, so the input is as well this matrix of visual regions. In a similar way, each visual region is a node. The relation is learned by the network. At the end, you have a matrix with this enriched representation of the visual regions.
Okay. Sorry, everyone, for the technical difficulties. All right, so let's start. Only 3 minutes. Perfect. So we will be talking about the syntax visual question answering, and I will basically be going briefly over the introduction, what is the syntax visual question answering, and the challenges that it introduces. And then we will go over the state of the art and how models evolved. And then we will briefly analyze the task and the main points of how hard this task is. So let's start with the definition. So first of all, what is a VQA? VQA stands for visual question answering, which is the task of given a question and an image, you have to answer basically, right? So in this example, who is wearing glasses? And this is the image, then the answer has to be man. And if this is the image, then the answer has to be woman. Right? Or is the umbrella upside down? The answer is yes or no. And it can be any type of question, right? It doesn't have to be yes or no. It could be anything about the visual scene, basically. Now, syntax VQA or text VQA is basically going on top of VQA and saying, okay, let's create a data set that takes into account the syntax in the images, right? So for example, what brand of alcohol is served at this establishment? And the model has to answer Guinness because Guinness is written over here, right? So it doesn't have to be necessarily the text in the scene. It can be also reasoning about the text. For example, what is the top O? So you have to know what is that, or what is the largest denominational table, right? So you have to read all of these and then realize, okay, probably it's 500 or something, right? So this is the new task, which we will refer as syntax VQA. But then the question becomes, but why do we need another data set, right? So what is the problem that the current VQA data set has, which we already have, I think, 5 or 6 of them. And the reason is, which I hope that you already learned by now, is that these models cannot read, right? They're illiterate, basically. So if you take a state-of-the-art visual question answering model, and if you just trained on classic VQA data set, and if you just directly test it on the validation, you just get 10%, right? And if you train this model, exactly the same model, on the text VQA, you get 13%, right? And this is another state-of-the-art NeurIPS paper, I think 2019. If you train exactly the same model, you get 12%, while humans get 85%. So we need to have a new data set, basically, to solve this problem. Now, obviously, this data set comes with a lot of challenges, right? And we will go over these challenges one by one now. So the first one is the open-ended vocabulary. In the classic VQA setting, you usually take the 5,000 most common words, and then you basically put a softmax at the end, and then you say, okay, you know what, classify me. But when it's text we are talking about, especially the scene text, right, you cannot get away with 5,000 most common vocabulary. You need to have an open-ended vocabulary. For example, in most of the time, most probably, you will not have 238 in your vocabulary. If you have 238, most likely you will have to have 239 or 345 or something like this, right? So you need to have a solution for this open-ended vocabulary. Next is the multi-word predictions. In the classic VQA, you usually have 1 or 2 word answers. Even if you have 1 or 2 word answers, it's usually, again, the 5,000 most common vocabulary words, right? Doesn't matter if it's 1 word or 2 word. So you don't even care about the multi-word predictions. But if it's a scene text, then now you have to take care of it, right? Because of the statistics of the data set. In this example, who wrote this book? And then the answer should be Edgar Rice Burroughs, right? So there's a lot of different statistics of this work. Next, obviously, since this is a scene text visual question answering, you need to do some scene text detection, right? So you have to realize where the text is, first of all, before even answering. And you have to extract the text, as Sergi mentioned in his OCR talk, right? And as he mentioned, OCR is far from solved. And if you see, for example, for us, it's very easy to read Crayola, even though it's upside down. But for an OCR model, this is Hebrew, right? So it's actually an interesting failure cases. And then next one is the reasoning. So if the question is how many pens are all these coins combined, first and foremost, you have to read the text, right? And you have to say 10 pens. And then you have to count. So basically say that, okay, these looks exactly the same, and there is 5 of them. And then since 5 over here, 5 over here, so 10, and you have the 10 pens, so it has to be 100. So there's a lot of different reasoning capacities combined together to answer a single question. And then you have the word knowledge. So you will hear a lot of word knowledge in the machine learning field, basically. And what we mean by word knowledge usually is prior knowledge, for example, things such as brand names or knowing what is a number or a license plate. Or these type of prior knowledge that we have, we don't even realize, we usually call them word knowledge. And you see that a lot in scene text, right? Because it's completely it's completely normal for us to ask something like which processor brand is featured on top left, because we know Intel is actually producing processors. But the person who doesn't know what Intel is at all, it's also as common as answering like Core 2 or Extreme, right? But because we have this word knowledge at the back of our heads, it's very easy for us to answer this question correctly. And we want these models basically to have this type of word knowledge at the end of the day. So now let's go over briefly how these models basically evolved, okay? So the first one, look, read, reason, and answer, also known as LoRA, is introduced by the TextVK paper. And it's directly taking the Pythia framework or Pythia model, and then just adding the OCR black box, extracting the features of the OCR text-wise, embedding it with fast text, and then running a contextual attention with a softmax at the end. Now, the interesting part is at the end of this model, okay? So the classic VQA model, as I already mentioned to you, is always uses a fixed vocabulary, usually 5,000. What they did is, okay, they said, you know what, let's add afterwards, after this vocabulary layer, copy module, also known as pointer networks, where we will also have a softmax distribution over these OCR words, right? Not only to the vocabulary, but to the OCR words as well, right? So then if the question is, what is the speed limit of this road? Then the answer or the model would just point directly to 21st and then MPH second, right? That is the idea of this model, basically. And it gives you 27% accuracy in the test set. Now, the next one, they still use the pointer networks, but with a caveat, with an important caveat that actually results in an important knowledge, right? So they also take the image encoding features, right? Visual features, and they also take the OCR features. So they run an OCR, they take the features of the OCR. But what they do is now use the spatial information that OCR gives you. Because when you run an OCR, automatically, not only you get the text, but you also get the bounding box information. So what they do in here is, if the Melbourne is over here, then we are going to get the fast-seq representation and then put exactly where this occurs in this matrix, right? So you concatenate spatially the visual features and then also the OCR features. And then you run exactly the same pointer network. So you still point to the OCR tokens if it's necessary, if it's in the answer. But instead of pointing directly to the fast-seq representation, you point now with the fast-seq representation plus the spatially location, right? So this is the most important point. And it gives you already 10% improvement, right? So the first lesson is basically spatial information is quite important, right, as expected. But this is what it shows, basically. Right? And it gives you automatically 10% improvement just by simply using the pointer mechanism at the spatial level instead of simply just running at the fast-seq level. And then next, Facebook came out with the next paper, which is M4C. I think it's called Iterative Answer Prediction with Pointer Augmented Multimodal Transformers for Text VQA. Since we all use transformers on everything nowadays, this is exactly what they did, basically. They take a multimodal transformer layers, actually initialized from BERT. We have seen and heard a lot about BERT so far. And they take the question word embeddings. So they take the questions embedded with the question word embeddings. They take the fastener CNN object features with all of these basically bounding box features with the ROI features. They also take the OCR features. Now, this part is quite interesting. In this part, they not only take the fast-seq representation of the string of the syntax, but they also take the phog, the bounding box information, and then the fastener CNN of the OCR tokens. So what does that mean? It means that if we have a bounding box over here, Aragon height, or 1 mile, right, then you would feed that location information and you extract the ROI features exactly of that location. So then they concatenate everything, right, of these OCR features. So the fastener CNN of the OCR, phog, fast-seq, and then the bounding box. You concatenate everything, embed it with a couple of fully connected, and then you give everything, dump everything to the multimodal transformer layer. Right? That's the idea. With the previous prediction embedding. So you start with a beginning token, and then you start basically everything attends to everything, right? So in theory, every one of these features will attend to the begin token, and then begin token will later on go into a dynamic pointer network, exactly like LoRa, okay? And then either select from the dynamic pointer network or select from the 5,000 most common vocabulary words, okay? That's the idea. So the lesson that we learn from this model is that whatever features you can find, just throw it into the transformers and see what happens. And it gives you quite a decent accuracy already. So that's the ideology or the methodology they follow in this paper. Now, next one is a CPR 2021 from Microsoft. In this paper, they follow and they completely separate the structure of the training into two. Okay, so first they do the pre-training and then later they do the fine-tuning. This is mostly influenced by the BERT, Albert, all of these Sesame Street characters, basically. We follow in this field for some reason. Anyway, so in this pre-training and fine-tuning, they always, for example, in BERT and Albert or T5 or GPT, they first do the pre-training with some kind of mass language modeling or denoising task, and then later on you do the fine-tuning on the downstream task. They do exactly the same now. They follow the M4C architecture. They just take that architecture and then do the pre-training and the fine-tuning. So fine-tuning is exactly the same way I just explained. So let's focus on the pre-training. So in the pre-training, one main difference is that they first of all change the input that the model accepts. So in the M4C, the model was only accepting in this part, string-wise, only the question. Now what they do in the pre-training is that they add the object labels because it's come free, right? When you run an object detector, and you also give the OCR tokens in here, not in here. Right? In the M4C, they were giving it with the old different OCR features. Now they're actually combining this with the question. And then they're running mass language modeling. Mass language modeling, where you corrupt the question, 1 or 2 words, the object labels, and then the OCR tokens. And first lesson of this model is that if they did not do this input, actually this model doesn't work, right? So it's very important how you actually select your input in a way that this pre-training strategy works. Okay, so that is lesson 1. And then the lesson 2 is that if you have pre-training plus fine-tuning on exactly the same data, which is on text VQA or STVQA, and do not use any extra data, you automatically get 5% improvement. Right. So these are the 2 very valuable lessons of this model, basically, that it teaches us. So on top of this mass language modeling, they also use image text matching, right, with a relative position prediction, where if there's 2 OCR tokens, you say which one is left of which and which one is right of which, or which one is basically up or down of which. Okay, so you're basically forcing the model to learn a little bit of spatial information. You're also learning which image and which text matches with each other. And you're also using the mass language model. Again, if you use this pre-training only on the syntax VQA or text VQA, you automatically get 5% improvement, right, without changing anything in the architecture. And at the end, if you use conceptual captions and all of these different data and concatenate them all together, then you can achieve actually 54% improvement, okay, accuracy. Right, and 50% accuracy in the STVQA dataset. So it's quite a bit of a improvement that you can get by following this architecture. Okay, now let's go into a little bit of the common failure cases of these models before we discuss the next model. So these models so far we have discussed almost always have the same problems, right? First one is the OCR errors, and we know that OCR is actually very faulty. At the word level, at the character level, it's not perfect, right? And if the OCR gives you something basically faulty, instead of giving you enter, if the OCR gives you center, these models have no way of fixing this error, right? Because they're just pointing, they're just copying. The next one is these models do not have very big capacity for natural language understanding, right? And then the next one is we still don't have any idea how to implement the word knowledge. We have no way of dealing with the complex layouts. For example, in this question, how do they move mountains? For example, in this one, it says, when you motivate me, I move mountains, right? So to answer this question, you have to first of all understand which layout does it belong to, and then have something like a semantic segmentation in a sense, and then try to answer it. And then, of course, there is a problem of long answers, which is the common problem of almost all these kind of like recurrent models, right? We always suffer from these long answers. Okay, so Latter, or also known as Literate, is basically trying to fix all of these problems following the same methodology that text-aware pre-training basically introduced. So they also propose pre-training and fine-tuning, right? But with a caveat. They do now the pre-training on something else. So before we go into that, let me first explain a little bit on how the architecture works. So this transformer encoder decoder is basically initialized directly from T5. T5 is a big language model which is trained literally on the whole internet. They scraped the whole internet from Common Crawl, which I think resulted in 40 terabytes, cleaned everything, 750 gigabytes of data, used denoising task, which we'll explain now, and then get that model. And then now if you fine-tune in downstream tasks, that achieves state-of-the-art apparently. So the more data, the better the model, it basically achieves the state-of-the-art. And so they use something called denoising task. It's very similar to mass language modeling. It's just that instead of just masking a single word, now you can mask consecutive words together. So in the mass language modeling, for example, you cannot do it. But in a denoising task, you can say, you know what, I'm going to just mask 2 of these tokens, and I'm going to ask my model to predict 2 of these tokens at the same time, right? And this kind of allows you to basically make the model's job a little bit harder so that it will learn a better representation, right? That was at least their idea. Now, in the Literate, basically, they do exactly the same, right? They take the T5 model, they apply the denoising task, but they also take something from what is known as layout LM, which Rubèn will explain later on a little bit more detail. But very briefly, they also use the bounding box information of the OCR with an NN embedding, right? A lookup table, basically, like a word-to-vec kind of ideology that is applied here, right? So you take the text embedding, and then you take the top left, and then bottom right information with a width and height of the bounding box. And then you embed, you sum everything up, you give it to a T5 encoder decoder, and then you say, now predict these OCR tokens, right? I masked a couple of them, and now you have to predict me these OCR tokens. And they do this in documents, right? That's the interesting part of this paper, I would say. Instead of using the OCR-CC, which is conceptual captions, which is the classic sceneries, right? Classic visual images, they take the OCR, they take the industrial documents library, and they pre-train on this. And the reasoning is that because if we need a model that is aware of the text in the scene, then we need to have images that has a lot of text in it, right? That should be text rich. But by definition, the scene text is not that rich, right? I mean, if you can probably see it, I don't know if you can, but 10% is basically 4, 5, and 6, and 50 plus is only 1 or 1%. And if you check over here, it automatically gives you like 80,000, which is more or less like 5%, so 535. So you get a lot of documents basically with a lot of text. Of course, by definition, you will have to get a lot of text in it, right? Now, in the fine-tuning stage, after they do the pre-training on the 70 million documents, now they do the fine-tuning. They use they replace the faster RCNN basically with a VIT. VIT is a vision transformer, which is a patch-based image classification network that is trained on ImageNet. And they take that model, and then they just, instead of using a faster RCNN, they just use now a VIT. Exactly the same word embedding we just pre-trained for, and then the question embedding that we just pre-trained for, right? So these are the things that is already pre-trained. We just take them, put the VIT at the end, and then now do the final fine-tuning. Now, I think mentioned, maybe I did not mention, this model already gets to 61%, right? 7% more. So the messages is basically that the documents apparently has some kind of a symbiosis or some kind of benefit to syntax, because we always thought that, okay, they are completely different, right? That they cannot actually even talk to each other. So that was the interesting part. And the second part is the importance of the language model, actually, how it affects the performance in the syntax visual question answering. Right. So now let's go to the couple of qualitative results of Literate and compare it to M4C. So as you can see that what kind of food is on the menu, this is a very text-rich environment, and you see that it automatically direct and correctly focuses on the right word. And what is the beer brand on top of shelf, on the top shelf right side of the image? So it kind of has a little bit of visual understanding, but we will come back to that. What is the beverage called? So it automatically does. Well, this one is actually interesting because even though the it's not a scene text, it's actually handwritten inside a scene, which is also an interesting case. It still gets it correctly, but we still have a problem when there is extremely complex layout where you have a couple of scene texts stacked on top of each other, and then you have to reason over it, right? So there's still a lot of things to go. Well, at least 40% improvement that can be gone. So now let's go into the deep dive analysis of the syntax visual question answering as a task and as a data set, right? So you have heard a lot of language talk, right? Demos talked about the Ashraf Bayram, basically the painter that can paint, and how blind people can learn visual appearances without actually knowing or seeing anything. So how is it possible? And we think that the perfect candidate for this phenomena is the language. So then the next question is obviously, how far can just language gets us in visual question answering, syntax visual question answering, right? So what happens if we just take a T5, pre-trained on C4, which is the whole internet, and then fine-tuned on SQuAD, which is a natural language understanding data set, and we just take that model, zero shot, just give the questions to this model with the OCR tokens. How much does this model get, right? And surprisingly, so Rosetta is the Facebook OCR, you get 16%. And if you make a little bit of better OCR, Amazon OCR, then you get to 22 almost percent. And with the GT, you get 25%. So 1/4 of the questions can be just answered without having any visual information at all. With just language, we didn't even do any fine tuning, right? We just said, let's have the natural language understanding, and then let's see how well are we doing in this task. So this tells you that, okay, natural language understanding at least has 1.25% importance in this task, right? Let's dive deeper, right? So what happens if we just do not give anything? Anything in the sense that we just give the question, right? We do not give the OCR tokens. We do not give any image, basically, image features. You automatically get 11%, which is kind of crazy when you think about it, just by the question. So this is kind of saying that, okay, there's something wrong in this data set, right? At least 11% of it. And then the next one is, what if we give the OCR, right, with the question, but no image whatsoever, and with image afterwards? So what is surprising is here is that visual features, in the sense of the VIT features or the faster RCNF features, doesn't really matter actually, only add around 0.5 to 0.6%, right? This is kind of crazy, which kind of makes you ask, is actually vision an artifact? But that's impossible, right? If it was evolutionarily, we would all be blind. So there must be something else that is wrong by these models that is doing, right? And according to our investigation, we realized that there's something not quite right with the data, right? So let's go, first of all, the question that require no vision. So for example, this is my favorite actually question, which says, have you tried this soda for this image? And the model says yes. Yeah, interesting. And it's correct actually, because most of the people actually answered yes. So it's considered as correct. And then the other one is the museum open? And the model still says yes, right? So this phenomenon already known in the VQA, the class VQA, because there was a data set imbalance between yes and no. And whenever there was a question, the model was automatically giving the yes, and it was getting like 70% in yes and no question. So we are kind of observing same phenomena here, right? So there's something wrong with the distribution. But there is more to it, right? Because we still couldn't explain how are we getting the 60% without seeing any visual feature whatsoever. So we said, okay, now what if we just separate the data set into 4 different categories? So we said, first of all, is a bag of words. I take an OCR and I just shuffle them, right? The second one is the ordered bag of OCR, which is every OCR has a reading order, right? From left to right, top to bottom, right? This is a given reading order. And then the next one is if we add the 2D spatial positions, and then the final one, basically, if we give the image, right? Everything together. So if we just give this model the bag of words, so if this hyperbarrier, and then we just give it automatically and shuffle all the words, then this model automatically gives 41% accuracy, because this model automatically already knows what is a website, and it doesn't need to look any of these, tokens at all. And then when you move into an ordered bag of words, so you actually keep the reading order that the OCR gives you, left to right, top to bottom, right? Then you automatically get 50%, right? Without any visual or positional information whatsoever. And after you add the position information, it gives you more or less 1%. And then it seems like after you put the image as well, you get almost 1% more, right? And obviously, we want the questions, or we want to evaluate our models for the final category, right? We want the models to take into account everything that is possible in the image. Otherwise, just answering the bag of words or ordered bag of words is interesting, but it's not the final goal that we would like to achieve, right? And it's really hard, actually, to come up with questions that require all of the different modalities that we have just, categorized. It's very, very hard. And the type of questions that we want to have is this type of questions, right? When it says, what does the red t-shirt say? That means you have to actually know what is a t-shirt. You have to get the layout of the t-shirt, and then you have to know which one is red. So you need to have the color information, and then read the text and answer me. Or in this case, what is in the bucket, right? So you need to realize it's a bucket, which is a 3D dimensional shape. And you automatically realize, okay, there is something inside the bottle, right? So you need to have this kind of word knowledge. And then also, not only the word knowledge, but what jersey number currently has possession of the ball, right? So you need to know what is the ball, and then you have to connect 2 different entities to say something like, okay, if this happens like this, this means it's a possession, right? or which is the can of Heineken, right? So not only reading the text, but reading the text and then reasoning afterwards. So these are the type of questions that we want, but it's very hard to basically come up with these type of questions. And currently, basically, this is what we are investigating, to have a little bit of better questions so that we can actually evaluate these models and realize the limitations better in that sense. So to conclude this talk, language is very essential as an indirect source of information and for word knowledge, right? And it's kind of shown from the language models that we use. Most likely, if you use a bigger language model, you will get even a better performance because they will be encoding the word knowledge even better, right? And the second one is a new symbiosis between the documents and the syntax is now possible, it seems like. So it opens actually numerous amount of possibilities, because usually the text, the document community and the syntax community doesn't really talk to each other in like sharing ideas wise. So now it seems like we can actually merge them together, perhaps in a single model that can do both VQA at the same time. And I would like to actually end this talk with a little bit of remark. So Mark Twain said, history never repeats itself, but it often rhymes. In the classic VQA, this actually happened. So when the VQA was first introduced in 2014, there was a next paper, 2015, saying that making, V matter in VQA. So it seems like we are actually looping into that direction again, right? So we need to make matter again in VQA, in syntax VQA, right? So that concludes my talk. If you guys have any questions or comments, I'm happy to answer. Is the vision transformer trained or freeze like faster or CNN? It is, it's both, but freezing results in better performance. Yes. Anything else? No? Okay. No worries. Luis, I think have something to say before we do a break. Luis?
Yes, thank you, Ali. Yes, so now we have a break, and I want to share with you some instructions for the practical session, which is the last thing we will do at the end of the session. Okay, so I'm sharing my screen with the instructions to follow this practical session. This is very basic instructions just to load the notebook that we are going to use in the practical session and to execute it. I can also paste this in the chat. It is important that you do it now because this notebook requires to download a very large file, and it takes more than 20 minutes to do that on Colab. So if you want to follow the practical session with the notebook open in your computer, you have to run these instructions right now during the break. Otherwise, you can also follow the session by looking at the screen, and I will explain the notebook myself. But if you want to play with it in parallel with the explanations, it's important that you execute the notebook before.
Hi, everyone. Am I audible? Can you see my screen?
Yes,
Yep.
okay.
Okay, thank you. So I'm Rubèn Perez, and I'm going to present visual question answering on documents, or as we call it for short, DocVQA. So as a little bit of context, as Dimos presented on Monday during the introduction, the document analysis and recognition field was one of the first ones who was dealing with text. However, their tasks were methods and were generally focused on information extraction tasks that aim to convert information in document images into machine-readable form, such as character recognition, table extraction. But the problem was that such algorithms were usually designed as task-specific blocks, blind to the end purpose the extracted information would be used for. And each of these tasks separately proved successful during the time, but where although we cannot consider it as solved tasks, nowadays are mature enough to go a step further. So in this case, DocVQA, what proposed was to condition this information extraction task to an end purpose driven by a user who requests some information in the form of natural language questions. So from the syntax visual question answering that Ali presented before, DocVQA brought the visual question answering task to the document domain. These are the different challenges or tasks that nowadays comprise document visual question answering, which I will go through one by one, where the reading systems must extract and interpret the textual content of document images in handwritten, typewritten, printed fonts, but also they must exploit other visual cues like layout or the document page structure, forms, table, and non-textual elements such as marks, tick boxes, or diagrams. Going to the first one, the single page document visual question answering. This is the task where, given a question posed over a scanned document image, the model must answer the question. So this setup of the task is exactly the same as in the syntax visual question answering, but where the questions are posted on scanned images instead of real scenes. So as I was saying before, this requires to exploit some textual content as the layout. For example, to answer this question, what is the invoice number? You need to understand this the form key value structure, or what is the description of the quantity. You need to understand this table structure and also these typewritten fonts. So it's quite tricky. Also, the diagrams for this question, what is the most critical live rep support? So you must understand the pyramidal diagram with this critical and the arrow from critical to non-critical. So it's quite complex. The dataset for this task is made of business documents from the UCSF Industry Documents Library, which contains many different document types, like, as you can see here, letters, form, reports, scientific reports. There are also some articles, emails, so it's quite varied, and it's ranged during the last 110 years, which conveys different challenges. This is the evolution of the state of the art on this task. This first initial attention was from the challenge held when the dataset was released. First of all, let me, these two couple of methods were explained, are multimodal transformer from syntax VQA, as Ali explained before. As you can see, you can use it also for document visual question answering. However, this doesn't work as well as other methods, especially designed for documents, because the challenges that the documents convey are different than the syntax ones. No, documents are usually much denser, and we have some complex layouts like diagrams or complex structures, which in syntax doesn't exist, although they have other challenges. This set of methods are one-dimensional sequence encoding methods that predicts the start and end tokens from a context, which are quite limited also. And then this late group are the two positional encoding methods, which combines also the semantics with the layout and also the image embedding. So it's are quite more advanced and complex, and the performance is also better. As I was telling you, this is the score. This is the NL score. Let me explain a little bit before going into the methods. This average normalized length time similarity. The insight beyond this is that if a method reasons correctly about a question and answers more or less correctly, but there has been an OCR error on the recognition part, it should be unfair to compare this answer to a method that answers something completely wrong. No, this would be the case of method B and method C. No, in the question, what is the number of the vote? If you answer everything correct, but you missed a number, it should be unfair to to score 0 this answer. So for this, they propose the average normalized Levenshtein similarity, which is based on the edit distance, normalized edit distance. So you are penalized for each character that you answer wrong. And I don't want to go into the details, but at the end, there is a threshold, which is usually set at 0.5, which we understand that if the edit distance is below this threshold, it's because the method didn't reason properly. So to avoid introducing some noise, because an edit distance of 0 is very difficult to obtain, just if you provide one correct character, such in this case, you will have very little score. To remove this noise, we set this threshold to 0.5. So if you score below this 0.5 threshold, the NLS is just capped to 0. So now I'm going to explain most of the interesting methods of this task. I would like to say that I will explain only the most interesting methods, but also there are you have to know that there are more than 1,000 submitted methods on this task, out of which 28 have been made public. However, for most of them, the authors didn't publish any papers. So even though they might have a real good score, some of them come from companies which they don't publish any paper and they don't provide any information. So it's very difficult to discuss about them. No, so I will explain only the ones that has a paper related to. So I can provide some details. So as I was saying, we have this couple of methods coming from the syntax visual question answering world. Then we have this one-dimensional sequence encoding methods that, as you have, we have been presenting during this couple of days, are based on the BERT architecture, which they just add a classification layer that predicts the start and the end tokens of the answer, given a context, which is just the concatenation of the OCR tokens in the ring order, from left to right and top to bottom. So these methods are very limited because the answer must be a part of the context, and then the one-dimensional layout information is also quite limiting. For this, there are the two-dimensional position encoding or relative attention bias that combines with image features, which are quite more interesting. So the first one, layout LM, uses a BERT architecture as a backbone. However, it adds two new inputs, embeddings. So from a document, they parse or run a pre-built OCR. They follow this classical architecture of BERT with the class token embedding and an embedding for each of the tokens. And they add the left, top, right, bottom embedding token layout information, and then they pass this information through the self-attention or the transformer network. On the other side, they run a faster RCNN to get the visual features of the regions of the OCR and aggregate them on the output of the transformer to then perform the downstream task. Also for the class token, they use the whole image, both for the layout position and for the image. So although this is very interesting, the visual features here are not part of the transformer, and then the semantics cannot attend to those features. So for example, if there are two visually similar words, this architecture cannot capture the relation between that words might have. For this reason, they propose the layout LM version 2, where this time they add the visual tokens with the information about this visual appearance of the document as independent tokens, as you can see here. Also, they introduce the layout information in 2 dimensions here, but also they do it in the attention scores of the transformer, which are not represented here, but they do. And then they pre-train this network on 3 different pre-training tasks the mask visual language modeling, which is similar to the one that Ali has explained. They mask one of the textual tokens, and however, they don't mask they mask also the corresponding image region to allow or to prevent the image to look at them. On the other hand, the text image alignment, what they do is to cover some of the text, as you're seeing here, at a line level, and for each text token of the encoder output, perform a binary prediction where it must predict if the token has been covered or not. Which this is very useful to align text, image, and position. And finally, the text image matching task replaces the image, these ones, by another one, and use the class, which is this one, to at the output of the transformer to predict whether the text is from the image or not. Finally, the tilt method uses a T5 as a backbone, but similar to layout LM version 2, includes learnable bias in the attention scores to also make the spatial reasoning explicit into the attention. However, in this architecture, they group the distance into 32 discrete buckets in vertical and in horizontal axis, which allows the model to group the tokens according to distance similarity groups. In addition, they use a contextualized visual embeddings. So they use a UNet, which provides access to the information near the neighbor information, visual information, but also to more distant regions of the page, which is quite important for example, descriptions of an image or something like that might not be really close to the corresponding image. So with this, they analogously to the word embeddings, they cover the image regions semantics in the context of the visual neighbors. They pre-trained this architecture on the text denoising task that Ali already presented. And after these methods, we asked, is the vision important in DocVQA? So as David Mar was saying, what does it mean to see? The plain man's answer, and Aristotle's too, would be to know what is where and by looking. So in other words, vision is the process of discovering from images what is present in the world and where it is. So yes, actually visual information has been always there. Offloaded to the OCR, which is tasked to answer both the what and where description, the bounding boxes coordinates are. However, the real questions are how good is the OCR and what kind of questions require further visual or reasoning, which is quite useful to see some difficult or failure cases. For example, this one, where it says, the question is, what is written in place of 34 8-point gallons, which corresponds to this. So we are asking, what is rewritten here, which is very difficult, because you need to understand what is rewritten. You have to replace this for some handwritten, very difficult to recognize text. And as you can see, many of all of the provided methods fail. Another example, diagrams are very, very hard to interpret for the methods. What is the dividend payout in 2012? If I give you some time, you would probably realize this is the dividend payout, which is 4,084. And all of the methods fails miserably. Also, to understand the layout, what is in the heading box, management advisory, which it's quite obvious for us, but you need to know what is a heading box. And as you see, most of the methods also fail. Another example, to understand if it was a separate fluid sample included in the document, this corresponds to a checkbox, which actually it's not perfectly checked, but still a human can easily answer this. The methods, as you can see, they cannot. So this is a breakdown of the results by question type. So question type means the type of data where the question is grounded. So as we can see, most of the methods have good performance of the same categories, while perform worse on others. This is because the kind of reasoning that is required to answer the questions is different, but also is highly correlated with the amount of available training data. Now, as we know, to train the methods are quite data hungry, so they need a lot of data to train. And this is when infographics visual question answering came in. In this one, it consists of much visually rich images with more plots, diagrams, and really complex structures like this one. And also, there are questions posed that require mathematical reasoning, such as counting, sorter, and also there are really complex aspect ratios, like these super long images that are not just big, so you can just resize. It's just a complex aspect ratio that you have to deal with that is very different to the standard A4 dimensions that we can find in business documents. As another example, just check on this question. How many companies have more than 8,000 delivery workers? Again, for humans, it could be super easy. It's just Canada Post, Amazon, so 2 companies. However, to answer this text, you need to first read the text, of course, but then you have to recognize the worker symbol, which is this one, identify the structure of the document, integrate the visual, textual, and structural information, perform a counting operation, also understand that 8K means 8,000, which is not trivial at the end, and do some kind of math. No? So these kind of questions and images are usually more complex. However, these last tags I will present are quite recent, and nowadays there isn't any method specifically designed to address the infographics complexity. Tilt, for example, that I explained before, is pre-trained, or they also evaluated on this task by changing the setup and the pre-training task. For example, they pre-train on infographics icon detection, but the architecture is exactly the same. So there is currently no specifically designed architecture designed to address the infographics complexity. That, as we have seen, it's quite hard. And I like to show you the comparison between the single page and the document and the infographics visual question answering tasks, and especially as we can see here, Tilt that is evaluated in both of the challenge, and there is like around 30 points of performance gap because of this complexity gap I was explaining before. No, so there's a lot of work to do there. I will present then another dimension that opens. No, so we have the business documents, then we move to more visually rich documents, and now we pose the question of what about posing the questions on a whole collection of documents. In these documents, document collection visual question answering is a retrieval style evidence seeking task where, given a question, the aim is to identify and retrieve all the documents in a large document collection that are relevant to answering the question and provide the answer. So, for example, in this question, in which years did unnamed rivers run for the state senator office, you have to first find in which documents did unnamed rivers run for the state senator office, which are, thanks to this evidence we have here, the ID, the document 454, which, as we can see, is this one, unnamed rivers running for the state senator office. And the answer is actually the year of the election date, which is 2016. So you have to scan or check or retrieve the proper documents where you can find the answer to a question, and then find the proper answer. No, so For this collection, the documents were sourced from the open data portal of the Public Disclosure Commission. All the scanned documents are the US candidate registration form, so it's the same form, filled in using handwritten, typewritten, or printing text. It's quite interesting because it contains checkboxes or signatures. And also some complexity it has is that, as we have seen before, sometimes the number of relevant documents we might have are 2, 1, up to 10, but there are some that are up to exactly 200. So this is something, a variability that methods has to deal with. However, as I was saying, also the current methods that we have nowadays are quite simple and work on 2 stages, where first they rank the documents according to the question, and then they answer the question with extractive methods from the most relevant documents. For example, the document retrieval method uses a very large train on classification task, and then use the logics to rank the documents, and finally extracts the answer with the doc reader method that was presented in the single-page document visual question answering. So as you can see, is these 2 steps. No, first get the documents and then get the answer. The Radar, for example, was doing something a little bit similar, using anchor boxes to extract 28 different fields, such as the candidate name, the candidate office, the party, or the election date, and then they got the answers with a very large model. So at the end, the complexity of this task relies mainly on the gigantic size of the collection, and currently methods are tackling it more in an engineering way than what we're used to seeing in research. The last one, the handwritten collections and visual question answering, it's also a collection-wise, but this time is in handwritten form. So in this one, the challenge is to retrieve a snippet of the document where the answer can be found. So the idea is not to first apply the OCR and then retrieve an answer, but directly retrieve a snippet of the document matching the question. There are 2, well, this task or dataset is composed of 2 different sub-datasets. One is this Bentham question answering, which is a real handwritten document collection, and the other is a rendered from Squad, which is an already existing extractive question answering dataset from the NLP, which we have they have rendered in images with some real smudges, as you can see here, to make the task a little bit more harder. Nevertheless, I would like also to introduce some task-agnostic document models, which they haven't evaluated for document visual question answering, but still I think are very interesting for the case that attaches. The first one is DocFormer, which is an encoder-only architecture, which the spatial and visual features are passed as procedural connections, as you can see here. And this is pre-trained on multimodal masked language modeling, which in this one, for example, differently than previous methods, they don't mask the image region to better align the image and the text. So to recover a masked token, they can attend to neighbor tokens, but also to the image corresponding to the part. Also, they pre-train on the learn to reconstruct, which is similar to an autoencoder method. The multimodal output of the DocFormer is passed to a decoder, which is tasked to reconstruct the masked image regions with L1 loss. And the text describe image task, where if they replace an image region, a random image region from the input, and then the task is to predict if a text token corresponds to an image region or not. Also, the self-doc is very similar. but the interesting part here is that they group the elements in semantic components. As far as we have reached here, they were also always treating each unit or minimal granularity, you want to call it, as the words, no, word by word. In this one, they group, as you can see here, by paragraphs or titles or dates. Also, they don't have examples here, but also I think tables or diagrams, which is a very nice approach, which they claim that avoids an overline fine-grained with excessive contextualization. No. Also, they treat textual and visual range separately to later fuse them in a cross-modality encoder, which is this one. And for downstream usage, they propose a modality adaptive attention mechanism for multimodal feature by adapting the general idea of this is to apply the same dependent attention weights to the two modalities to emphasize or diminish the intensity of language or vision features dependingly on the kind of document that they are tackling. For example, if a document contains handwriting, which is very hard to recognize by the OCR, in that case, it will make stronger the visual clues. While if the document contains a lot of easily readable text, then they will emphasize the textual part. Finally, the donut method is a method that has a holistic representation of the whole document, because also as up to this point, all the methods were using a pre-trained OCR or pre-trained OCR, which they were not backpropagating or fine-tuning. So here they don't use OCR per se, which we can say that they are learning to read also. And they model the whole input just from the visual entities. So that's all up to the models. But there is one last thing. We have been talking a lot of pre-training tasks or strategies or pre-training datasets. So I would like to just give a really brief details or analysis of them. We have, for example, RVL CDIP, which self-doc and tilt are trained on. This has some the annotations of this dataset are the document class. Also, there is this IIT CDIP dataset, which the layout LM v2 and the former methods were pre-training on. This has the text annotated from an unspecified OCR, so there is no layout information, and the transcriptions of the OCR are quite poor, honestly. Then there is this IDL, which some methods pre-train on them. However, the annotations actually then are exactly the same of the RVL CDIP, of the IIT CDIP dataset, but these two methods pre-train on a new OC or new extracted OCR, which is quite better. So this is why I wanted to give a look of this OCR IDL, which they have the text and bounding box from Amazon TextTrack and the document classes. So actually, as I was saying, let's say those datasets are not independent. Actually, this IIT comes from the old tobacco legacy document library, which now is part of the whole IDL. The RVL CDIP is part of the IIT dataset, and the OCR IDL is extracted from the IDL, which also is the source of the DocVQA dataset, for example, the single page, and has an intersection of IIT and RVL, and is currently the biggest document dataset with high quality OCR recognized text and multi-box. So is nowadays quite worth to pre-train on this kind of datasets. No, as we have seen, all of the previous methods, layout LM, layout LM v2, tilt, donut, self-doc, docformer, also Literate from syntax, are pre-training nowadays on lots of documents. So these are an interesting thing to keep an eye on. And just to finalize, these are the future challenges related to document visual question answering. First of all, the explainability, no? So finding the evidences to the answers are very important. Actually, this is extensible to many other tasks, but here we have seen that language helps a lot, and in some abolition studies, actually Ali has shown you before that only with the questions, some models were able to score up to 10% of accuracy. So explainability is very important. Also, the privacy preserving methods. So it is possible to train with private data. There are a lot of companies who have a lot of data they cannot share. So can they train these methods, and then what can they do with these methods? For example, as same as before, no, some methods answers just given by the knowledge they have learned before. So how much does the model know already? How much does it extract from the documents at hand, and how much does it base its answer on the previous knowledge, and how much in the image provided? No, you don't want to someone to ask some question about some client you might have, and then the answer the model answers correctly some kind of sensible data, no? So it's quite tricky. Also the scalability, no? So move from single page to multi-page documents or to document collections. As we have seen, we have 14,000 document collections. It's very hard to tackle by just engineering stuff problems. Also, what about complex or mixed documents such as comics or maps, engineering drawings, musical scores? It's very important also the external knowledge, no? Sometimes we see it as something bad because we cannot say that there is a kind of explainability, but on the other hand, it helps us to answer some kind of questions, no? In the one of the images Ali was saying, was showing, if I asked you what is the Heineken beer or whatever, you need to know that Heineken is a beer, or beer usually goes in a can, so it's quite important. And finally, multilingual. Multilingual is very important in many natural language related tasks, also for documents. So this is a very important thing to consider for the future. Thank you very much. Does anyone have any question? So thank you very much. If you want, yes.
Yes, thank you, Rubén. So we are going to start now with the last part of today's session. Can you see my screen?
Yes, we can.
Okay, thank you. So, well, I hope the ones of you that want to be running the notebook at the same time during this practical session have already loaded and executed the notebook. As I said before, it's not mandatory. You can also follow the practical session just by following my explanations and looking at my screen. But I think it's also worth to play a little bit with the model by yourself. So, okay, let's start. The idea of this part of the session is that we wanted to finish the course with some practical stuff. The intention of this part is basically for people who has never worked with multimodal architectures and especially using textual information combined with visual information. So if you are in this situation, I think this is an interesting part for you because the model that we are going to use is a very simple model, but it's the starting point to build more interesting things on top of it. The idea is that we are going to build a simple multimodal transformer for the context dataset. If you remember the last session you had on Monday about fine-grained object classification using a syntax, you remember that you had, or Andrés explained to you this context dataset. Basically, what you have here is a set of images that are a subset of images from ImageNet. All of them belong to the classes building and business places from ImageNet. But now here you have fine-grained classification over them that, for example, is able to classify the images between different specific business places or different types of buildings, let's say. In total, there are 28 categories, fine-grained categories in this dataset, like, for example, bakery, bistro, restaurant, cafe, or pizzeria. And we have around 24,000 images in total, right? So not all the images in the dataset have text. This is an important detail. But when there is some text in the image, usually this text is going to be very useful for the classification task. Let's just take this image, for example. Looking at the visual content, it's quite difficult to distinguish this business between a bakery or a restaurant or any other kind of shop, right? But once you have the word, or in this case, the name of the business, and you can recognize it, you can use this semantic information to make the classification. So we cannot rely only on textual information because we have also images without text, but when there is text, it's supposedly to be useful for the classification task. Now, the model that we are going to use for this task is what you can see here in this illustration. We can describe the model at a high level before we go to the code, just to understand a little bit how it works. As you can see, from the input image, the first thing that we do is to extract visual features with a ResNet, CNN, and textual features. The textual features, we extract them using a pre-trained OCR model. And for each word detected and recognized by the OCR model, we embed it using the fastText word embedding, right? So these models that you see here with a dashed line are models that we use pre-trained and that we don't fine-tune for this task. We just use them as feature extractors, as I said. In the case of the ResNet, what we use as features of the image is the last feature map of the last convolutional layer, which gives us a feature map of 8 times 8 times 2048 features, right? So we have a grid of features of 2048 dimensions. Now, each one of these features is going to be one visual token that we input to our transformer model. And on the other hand, for the textual modality, for each one of the N words provided by the OCR, we embed them to the fast text embedding space. So we have for each word 300 dimension feature, right? Now, if we want to input all these visual and textual features all together into the same transformer, we need first to embed them to the same dimensionality. And this is what we do in these linear projection layers. So basically just projecting visual and textual features into the same dimensionality. So now we can feed them to this transformer encoder, right? Together with the visual and textual tokens, we also feed one special token, which is this CLS token here. And the output of the CLS token is fed into a final multi-layer perceptron head that takes the output of this CLS token and predicts one of the output classes while using a softmax operator, right? So this is the model that we are going to code right now. So the next thing is to take a look to the code directly. Okay, first we have here some imports, but nothing really important. And the next thing we do in this cell is to load the fasttext model. And this is actually the part that takes a lot of time in Colab. I recommended you to run the notebook before, because the model of the fasttext that we are going to use, the fasttext embedding, it's like 6 GB of memory, and in Colab we have very limited bandwidth, so it takes a lot of time to download this. Obviously, if we have a persistent hard drive, we don't need to download this every time, but in Colab this is not possible, so we have to spend all this time just to download the fasttext model. And the next thing that we do here in this cell is actually to define the architecture that we are going to use for the context transformer. So let's take a look line by line what we are doing here. First, in the constructor of this context transformer class, and then we will take a look at the forward method. In the constructor, the first thing that we do is to create the visual feature extractor that, as I said before, is a ResNet 50 model. In this case, we have to load the pre-trained model of ResNet that has been pre-trained for image classification on ImageNet. And since we want to use the last output of the last convolutional layer, we need to remove the last 2 layers of the ResNet. We are going to do it in this line here. The last 2 layers in ResNet, as you know, are the fully connected layer for classification and global average pooling layer. So we just remove these 2 layers, and now our visual feature extractor is just all the convolutional layers in a ResNet up to the last one. We also set the requires grad attribute to false for all the layers in this ResNet model, because obviously we don't want to train it. We don't want to update this model during training. But anyway, this is not really important because now we are going to do only inference with the model. But if you want to train it, it's important to do this step. And by the way, remember that also in the GitHub repository of this practical session, you have the script to train the model if you want. Now we are going to use a pre-trained weights, but if you want to train it from scratch, you have the script in the GitHub repository. Okay, now we define here some constants for the dimensions of the CNN features, as I said before, 2048 for the visual features and 300 dimensions for the fasttext features. We also have another constant here, which is the number of tokens number of visual tokens at the output of the CNN of the ResNet in this case, which are 64. Remember that we have a grid of 8 times 8. And obviously, if we change the feature extractor or the model that we use for word embedding, we have to change also these constants. Now, the two linear projections, these two layers that we have seen in the diagram, these two linear projections are just two fully connected layers that are defined here. Okay, in the case of the visual embedding, we are going from 2048 to some fixed dimensionality that will be defined when we create the model. This is a parameter of the constructor. We are going to use here 256 or 512, for example. And in the case of the textual features, the linear layer goes from 300, which is the dimensionality of fast text, to the same dimensionality. And this same dimensionality is going to be the dimensionality of the inputs in our transformer model. Okay, now here we have the positional embeddings for the visual features. This is not really critical for our model, but I consider it somehow interesting to add it because you maybe need it in the future. If you take a look, for example, at how the Vision transformer works, in here what they do is to split the input image in patches. So each one of these patches is going to be one input into the transformer encoder. And for each one of them, they add this position embedding, which in their case is just a single scalar, a number, that indicates the position of each of the patch, right? So in our case, we can also do that, but in some Vision transformer models, we also use learnable position embeddings, which is what we are going to do here. So we create a set of parameters. Each one of them is for each one of the positions in the visual tokens. Since we have 64 tokens, visual tokens, we need one position embedding for each one of them. And in this case, our position embeddings have the same dimensionality as the input to our transformer, right? We add another position embedding here for the CLS token, which in our case is also a parameter. So the CLS token in our case is not a fixed predefined vector, but it's a parameter. So this means that the model, while we train, is learning the best positional embeddings for the visual features, and also is learning some representation for this CLS token that is useful for the classification task. As I said before, this is not critical for our task now, because actually this model is trained with very little data. So my assumption is that the position embeddings that we will learn are quite constant for all the embeddings except for the CLS token. But in case you want to play with positional embeddings, you have already these parameters ready here. Okay. Now, finally, we need to code here the transformer encoder. And in this case, what we do is to use the built-in transformer layers in PyTorch. If you want, I recommend you to take a look at the documentation of these PyTorch transformer layers after the session of today, because it's very well explained how they work. But in here, if you look at the code, basically what we do is to create a template for the encoder layer. And then the transformer encoder will be basically a set of repeated transformer layers one after the other. Okay, so basically we create a transformer encoder layer with the input dimensionality that we specified at the constructor of the class, with the number of heads that we want, with the feed-forward MLP dimension, which would be this MLP here. We can also choose the dimensionality of the output of this MLP. And we add also a layer norm layer after each of the encoder layers, right? So then we create the transformer encoder by stacking several transformer encoding layers, and the number of layers that we stack is also a parameter here in the constructor of the class. Okay, so now the last thing that we need is the classification head, that, as you have seen in the diagram of the model, takes the output of the feature of the CLS token and predicts one of the output classes. So now here, as you can see in the code, what we have is a sequential model with two linear layers. The first one with a ReLU or a GeLU activation function, and the last one without any activation, because here is where we apply the softmax to make the final prediction. Okay, so now let's take a look quickly at the forward pass of this model. It's very intuitive. The first thing that we do is to process the input image. As you can see in the forward pass, we provide the image and also the text features. As I said before, the first thing we do is to process the image with the ResNet. Then we do this rearrangement to have a sequence of 64 visual tokens. And then we process all these visual tokens with the first linear projection, the visual embedding. Right. The next thing we do is to prepare the CLS token. The CLS token is the same for all the images in the batch, so we need to do this expansion here. We have a single CLS token, and we want now to expand it to all the images that we have in the batch. And then we concatenate this CLS token with the visual features, right? And we add the positional embeddings. Remember that these positional embeddings are parameters, learnable parameters that we are learning while training. But at the end, what we want to do is to add these positional embeddings to each of the visual features and also to the CLS token. Then we process the textual features. These are fast text features with the second linear projection and embed them to the same dimensionality as the visual features. And then we concatenate CLS token, visual features, and textual features together. And all these tokens are fed into the transformer in parallel. Now, from the output of the transformer, we are only interested in the CLS token output. So we have to select this CLS output and process it with a multi-layer perception head, which is what is going to give us the classification output. Okay. Up to here, it's everything clear. I don't know if someone, sorry, have some question up to this point. No? Okay. Oh, I see someone is having an error here, but I'm not sure.
He said that it sold afterwards, Luis, at the end.
Okay.
Yeah.
Well, it may be just that the download failed while you were downloading. As I said before, the problem here is that in Colab we have very limited bandwidth to download these files, and probably something happened while you were downloading. I don't know if anybody else has had this problem or. Just happened to one person. No? Okay, maybe just trying it again and see if you can download it correctly. Okay, so if there are no questions with the model, I think here we have all that we need now to understand it. You have seen that this is a very simple model. I forgot to mention some things about the design. The first one is why we are using a fast text word embedding. We can obviously use any word embedding, but as you have seen in the previous lectures or the previous presentations of this course, the fast text word embedding has a very interesting property, which is that it's able to encode out of vocabulary words. And why are we interested in encoding out of vocabulary words? Because most probably our OCR module is not going to provide us with perfect transcriptions of the text that is in the image. So if the OCR model makes some errors in some of the characters of a given word, we can still embed it using the fast text. We can also use other big language models to do this embedding. So for example, we can use here a BERT model, but it's not really necessary because in a syntax, usually we have sparse words in the image. So we don't use to have large sentences. So the context in which the words appears is not critical for this particular task. You think about it, basically in this task, we are interested in finding maybe one word that is specifically containing some very useful information to identify the class of the image. So we will not see a lot of benefit of using a BERT embedding here. It's different in the case if we have a third modality, for example, with a question, where we have then a sentence with a very well-structured order. And in that case, it's obviously recommended to use a BERT embedding for encoding this third modality if we are doing visual question answering. But for the fine-grained classification task with the fast text, we are doing well. And I also didn't mention that this simple model is getting quite good results on the context dataset. It's not a state-of-the-art, but I think we get close to 84% accuracy on the context dataset, which is a very good accuracy. Okay, so now if you understood how the model is built in this cell, now the next thing that we have to do is to load the pre-trained weights. As I said, I trained this model before, and you can download these pre-trained weights, or also you have the script to train the model by yourself if you want. But now for the moment in this session, we are using the pre-trained weights. Now, the transformations that we use for the input images are very basic, just resizing the image to a fixed size, 256, and we are going to use the center crop of the image. Another strategy would be to use multiple crops and then average the classification output in case we have different aspect ratios would be a good strategy, but as a simple transformation, we will go for a center crop in this case, and then we do the normalization. Now we have here also the class labels for the 28 classes in the context dataset. And in here we define a method in which we input an image file name and the OCR tokens that we have detected on the image. And as you can see, what we do here is just to apply the transformations to the image and process each of the words that we have detected with a fast text word embedding, so that we can directly now call to our method, passing the image on one side and the fast text representation of all the text that we have found. And the output of this method is the classification probability distribution. Right, so we have everything ready. Now the next thing we can do is to start playing with some images and see how is, for example, the effect of using the textual information or not. For this first experiment or for this first demo, we are going to use this image that you can see here. As you can see from the visual information, it's very difficult to discriminate between a bakery or a restaurant, for example. The visual information is perfectly compatible with a restaurant or even with a pizzeria if you want. So the key to classify correctly this image will be, as you will see, to correctly use the textual information. This is what we do here in the next cell. And for the moment, we are not going to use the OCR. We are going to just simulate the OCR tokens with a list of words. So we can, for example, do this kind of experiments. Now, what happens if my OCR doesn't read anything in the image? So we have an empty list of words. And what happens if I have a perfect OCR that provides me with the 3 words in this particular image perfectly transcribed? If you execute this cell, you will see that the prediction without text is wrong. In this case, it predicts the image as a dinner place, while if we have a perfect OCR, the model is able to correctly classify the image as a bakery. Okay, so now the next thing that you can do if you want to play a little bit more with this idea is, for example, to use other images that you can download from the internet. Or also an interesting experiment is to play a little bit with the output, with the simulated output of the OCR. Let's try what happens if the OCR makes an error in the bakery and changes one of the characters. No? So these kind of things you can do it easily by replicating this cell by yourself. And since I'm going out of time, I'm not going to play with it, but I encourage you to do it by yourself. And what I'm going to do is just to explain these last cells that we have here, which adds the OCR model. So we have the fully functional system for this demo. The OCR that we are going to use in these cells is the Easy OCR system. This is an open source, it's an open source project that integrates different text detection and text recognition models. And it's very easy to use. You have just to create the reader, specifying which is the language that you want to recognize in the image. And then the only thing that you have to do is to pass the image to the reader, and the model will provide you with the bounding boxes, the words that it has recognized, and the confidence values for each one of the words. Okay, so now just with this simple method, this detect text method that we have outlined here, we have the fully functional system that, given an image, first detects the text in the image using Easy OCR, and then, oops, I've been disconnected from the collab. But anyway, we are just finishing. Now we are running the same inference process that we did before, but now this OCR tokens list that we were simulating before is actually the output of the Easy OCR system. right? And in this case, you can see, for example, even that the OCR has made some errors in the name of the business in this case, which is not really important. The bakery word was correctly recognized, so the model in this case is correctly recognizing the image as a bakery. And yeah, we can see that the model is correctly using the textual information in this particular image. I recommend you to play with different images. You will see different behavior in different cases. You may find some images like this one. For example, if you look for dinner images in Google Images, you can easily find images like this one, for example, in which the text is providing us with some useful information. Also, other images you can try with images that have no text or have directly some distractors and see what happens. If the model have also learned to discard this non-relevant textual information, or other images where, as before, the textual information is going to give us useful information for the different classes in the context transformer. So this is the end of the practical session.